Inside your computer, billions of microscopic switches decide everything you see, hear, and do.
The CPU acts as the brain of every modern electronic device, controlling and coordinating all operations. Without a CPU, a computer cannot think, calculate, or respond. Modern CPUs are built from billions of microscopic transistors, acting as tiny electrical switches.
Dozens of ultra-thin wiring layers connect billions of transistors inside a single CPU.
Together, these components allow CPUs to perform trillions of operations every second.
From the moment a device powers on, the CPU works relentlessly, without rest.
Each transistor acts as a microscopic switch, turning electrical signals on and off.
Modern CPUs are built using dozens of microscopic layers stacked with extreme precision.
Hidden beneath the surface, the CPU silently powers the digital world.
In the early days of personal computing, processors were simple, yet revolutionary.
The 6502 processor became one of the most influential chips in computing history.
With only a few thousand transistors, early CPUs laid the foundation for modern computing.
Despite its limits, the 6502 powered an entire generation of computers. By modern standards, these speeds seem slow, but they once changed the world.
These simple processors brought early video games into homes around the world.
High-resolution graphics were impossible, but creativity flourished within limits.
This simple processor became the foundation of an entire generation of computing.
Though simple by today's standards, the ideas behind early CPUs still shape modern computing.
Good architecture allowed simple processors to achieve remarkable results. Separated by decades, these processors share more in common than it appears. Despite massive differences in power, all CPUs share the same core design principles. What once required thousands of transistors now uses billions.
The same logic gates power both early and modern processors. Only the scale has changed.
Though vastly different in power, both CPUs exist to execute instructions.
The instruction is the same. The speed is not.
In just decades, computing power increased billions of times over. The cycle remains the same, but the clock runs millions of times faster.
The same principles that powered hobbyist computers now drive artificial intelligence.
Across generations and technologies, the foundation of the CPU remains unchanged. Modern processors deliver performance once thought impossible. With billions of transistors, modern CPUs operate on an unimaginable scale.
Modern CPUs perform trillions of calculations every second.
Modern processors make immersive 3D worlds possible.
Artificial intelligence relies on the immense power of modern processors.
Modern CPUs manage dozens of tasks simultaneously without breaking a sweat.
Despite decades of progress, The core design of CPUs remains unchanged.
Regardless of size or power, CPUs follow the same logical principles.
From early processors to modern AI chips, the same DNA persists.
CPU evolution is not reinvention, but refinement of a timeless design. Beneath its exterior, the CPU reveals a carefully layered design.
The interposer connects the processor to memory and the rest of the system.
The heat spreader protects the CPU by efficiently dispersing heat. Thousands of microscopic connections allow the CPU to communicate at incredible speeds. The silicon die is divided into specialized regions, each optimized for a specific task.
At the core lies the silicon die, the true heart of the processor. Each processing core is itself a complex system of smaller functional units.
Cache memory keeps critical data close to the processor for rapid access. Modern CPUs integrate graphics processing directly onto the silicon die. Every layer and region exists to move data faster, compute accurately, and perform efficiently.
To understand the CPU, imagine a powerful calculator placed on a desk. The desk represents the CPU's limited internal working space. The arithmetic logic unit is where calculations and logic operations take place.
Beyond math, the ALU performs logical decisions and comparisons.
Simple arithmetic operations form the foundation of all computation.
Registers are tiny storage locations designed for maximum speed.
Registers are faster than main memory because they live inside the CPU core.
Registers are incredibly fast, but their size is extremely limited.
Together, the ALU and registers form the fastest path for computation.
This is where the CPU thinks fastest, inside the ALU and its registers.
The program counter keeps track of which instruction will execute next.
After each instruction, the program counter advances to the next address.
Jump instructions directly change the program counter to a new address. Conditional branches allow the CPU to make decisions. Not all programs execute in a straight line. IF statements are implemented using conditional branch instructions.
Loops allow instructions to run repeatedly until a condition is met.
FOR loops use comparison and branching to repeat instructions. When the condition fails, the CPU exits the loop and continues forward. By controlling the program counter, the CPU controls the flow of every program. Every instruction follows a repeating cycle: fetch, decode, and execute.
During fetch, the CPU retrieves the next instruction from memory.
The fetched instruction is stored in the instruction register. During decode, the CPU interprets what the instruction means. The control unit prepares the CPU to execute the instruction.
During execution, the CPU performs the actual work.
Arithmetic instructions are executed inside the ALU. Logical instructions determine program decisions. Fetch, decode, execute. This cycle is the heartbeat of every processor. Once execution ends, the cycle begins again. Some instructions must access memory to read or write data. Load instructions retrieve data from memory into the CPU. Store instructions send data from the CPU back into memory.
Accessing memory takes longer than working with registers.
During writeback, the CPU stores the result of execution. Writeback makes results available for future instructions. Memory and writeback serve different roles in execution.
With writeback complete, the CPU prepares for the next instruction.
Once memory and writeback are done, the instruction is complete. Memory and writeback ensure data is stored and ready for what comes next.
The CPU clock sets the pace for every operation.
Higher clock speed doesn't always mean better performance.
Clock speed is measured in cycles per second, known as hertz. Pipelining allows multiple instructions to be processed at once. Each pipeline stage handles part of the instruction.
Pipelining improves throughput, not individual instruction speed.
Modern CPUs work to keep pipelines full and efficient. Pipeline hazards can temporarily slow execution. Performance depends on both clock speed and intelligent design.
Modern CPUs achieve performance through precise timing and efficient pipelines.
Modern computing is shaped by two fundamental design philosophies.
RISC focuses on simple instructions executed at consistent speed. CISC packs more work into fewer, more complex instructions. Both approaches solve the same problem in different ways. RISC designs prioritize energy efficiency and predictability. CISC thrives where backward compatibility is essential. Today's processors blend ideas from both worlds.
Different designs, same goal: efficient computation.
From thousands of transistors to billions, the journey continues. Invisible, relentless, and essential, the CPU powers the digital world.